Yes, hello everybody, and thank you for attending my talk, a simulator coupling architecture for the creation of digital twins. We at Fraunhofer ISE, we do research regarding virtual engineering, in particular the coupling of simulators. And I would like to give you some insights into an architecture work that is ongoing in our place. And of course, I would also like to present some of our results. My name is Thomas Kuhn. I'm heading the Embedded Systems Division at Fraunhofer ISE, and I hope that you will be enjoying my talk. So, in this talk, we will be focusing on the simulation of systems So these are pretty complex scenarios, and I have created a small exemplary scenario for you with the idea of explaining our research goals. So here we see an excerpt of a city with cars and with pedestrians. I think the cars can be spotted easily. The pedestrians are the small blue dots. The idea here is to evaluate wireless communication performance. For example, to evaluate the question on whether we need an individual frequency band due to interferences, for example, between the cars and between the mobile phones of the pedestrians, or whether we all can be using the ISM band. The idea is that such a scenario requires simulator coupling. We need, for example, the ability to integrate applications. We need movements. We need physics so that we see if a car brakes sufficiently fast. We also need, for example, for the pedestrians, the simulation of cell phone apps. We need a baseband and simulation, and we need the wireless channel. And now we could think of several concrete scenarios that we are evaluating here. So for example, in the large scale, we could evaluate movement patterns, we can evaluate traffic, we can evaluate, of course, network communication, and we can evaluate whether the communication channels have sufficient capacity. In smaller areas, for example, in the dotted area that I'm showing here, we evaluate the network performance on the baseband layer. And of course, we need a much more sophisticated simulation. So we need a much higher accuracy with our simulation. The creation of these simulations today is pretty challenging. Why is this the case? Many simulators that we are using for creating an integrated simulation, they are specialized. We have, for example, specialized network simulators. They provide a frame level simulation, and they are very good in the simulation of protocols. The simulation of baseband is Medicore. Usually this is a statistical model. They also have some capabilities regarding the simulation of movements. And there are some application models available. If we want to connect a real application, more sophisticated movement models, or maybe a very accurate baseband simulation, then we need multiple simulators. And then we enter this field of simulator coupling. So if we want to evaluate a system of systems, we have to couple a simulation for everything that has an impact on the system. And with complex systems, maybe safety critical systems that have hard deadlines, it's not sufficient to only simulate physics. We also have to simulate communication, maybe several communication technologies, and we have to simulate platforms, execution platforms, because they also induce delays. Today, simulator couplings are tailored. Simulators are not like software components, so every simulator has a very specific interface. I call this a syntactic interface because it's like a software interface that I use to interact with the simulator. For example, when telling him, okay, next step should be started. And of course, the simulators have execution models. These execution models are a little bit more standardized, I would say. It's not a formal standard, but there are several execution models like discrete time, discrete event, or continuous time, which are very well known and which many simulators implement in a similar way. So a simulator coupling usually requires effort for both the semantic coupling, so the integration of the models of execution, and the syntactic integration. Coupling frameworks support the semantic coupling. So it's possible to integrate the execution models, the models of computation and communication. That always yields a coupling error. This comes from the coupling, and the coupling error can be managed, for example, by adjusting the simulation step size, so the time that every simulator calculates before everything is synchronized again. The creation of these simulator couplings is a manual task because we don't have universal simulation components. So how can we enable a better reuse here? One technology, one standard that has been created in the past is the functional mockup interface. The functional mockup interface encapsulates simulation models into reusable functional mockup units, for short FMUs. These FMUs have input and output ports. Some have, in addition, configuration ports, and this functional mockup interface has been developed with the functional simulation in mind. So when I look on a car, for example, with a functional simulation, I have the functions of the car, I have the environment. I usually don't have a platform simulation. So the functional mockup interface focuses on this functional simulation, and it supports several other things. So for example, it provides an interface for the handling of numeric events. Those are, for example, discontinuities in a differential equation that require special attention. Normally, the simulation has to be re-evaluated at the times when these numeric events happen to provide a sufficiently accurate simulation. The functional mockup interface does not say how the simulation host that couples the functional mockup units into a simulation has to handle that. It just says it needs to be handled, and it provides an interface to access the necessary information, for example, about numeric events from the functional mockup units. Our proposal is to extend the functional mockup interface standards with additional properties for simulation models so that they become simulation components. A simulation component encapsulates a simulation model. The properties that we define in our architecture framework, they are independent from actual coupling semantics, and of course they are also independent from specific simulator coupling frameworks. These properties describe the encapsulated simulation models and help people to create coupled simulations by instantiating the simulation components. So first of all, we define message types that we annotate receive and transmit ports with. Functional mockup interface defines value types, so for values that are exchanged between ports, we extend this concept with message types. So we exchange typed messages between ports, which enables us to transmit or receive multiple message types and also multiple message instances per simulation step. A second major extension that we do is we create views. A view is, like in the architecture, a view on a specific simulation component, and every view exposes a specific capability of that simulation component. We define provided and required views, and every view has a view type. Here in the example, it is shown, for example, that we have one view type that is called node position, node pos, and a second view type, Chan Wi-Fi. The node pos view type communicates node positions. Here, this is a required view, so it receives this information from some other simulation component that provides node position data, for example, by simulating a movement model. The second view implements the simulation of a Wi-Fi channel. Every view has a defined simulation model, here shown in brackets. So the Chan Wi-Fi is discrete event simulation, DE. The node position is discrete time simulation, DT. Every view has a model of computation, and the coupling framework has the duty of integrating these models of computation with each other. These views, they define reusable interfaces. The idea is that a simulation component view acts like an interface. It should focus on the simulated aspects and not on the specifics of the simulation model. So the view is like a contract between the simulation component that provides this view and the simulation components that require this view. And that is exactly like in component-based software engineering. Views should generalize interfaces for common simulation models, for example, for node movements, for wireless channels, for protocols, and for much more. If we are able to create a generalized set of interfaces for simulation models, and if we are able to encapsulate existing simulators and their models with these views as interface, then we can enable a much better simulation model reuse and also the substitution of simulation components. So for example, if you need a more accurate simulation regarding the baseband, you could change an existing stochastic model exchange the existing stochastic model with a more accurate baseband model that provides a much better simulation, but also requires a higher amount of resources. This is a more advanced example from our paper. So here we are showing a simulation stack that consists of several integrated simulation components. So we have applications with a defined interface, we have protocols, we have a Wi-Fi stack, and we have the Wi-Fi channel simulation. But on the other hand, we also have the pedestrians with a traffic generator that resembles the smartphone applications, with a simulated Bluetooth stack, and with the simulation of a baseband that evaluates the interferences between both stacks. So what is our mission? The age of coupled simulations has just begun. Today, simulator coupling in industry is used, for example, for substituting expensive hardware-based test beds, for example, for hardware-in-the-loop testing. Doing virtual hardware-in-the-loop testing is much cheaper, but that is only the beginning. In the future, we will see much more autonomous systems, cognitive systems that need to operate in a variety of environments. And the development and testing of these systems is not possible without virtual test beds, because it is simply not possible to create such a large number of hardware-based test beds so that we can evaluate every meaningful situations that are relevant for these systems. We therefore need a way to rapidly instantiate simulations. And because the simulators are specialized, this will be simulator couplings. Today, these couplings need to be created manually. This is very expensive, requires lots of time, not only for developing, but also for validating. And that obviously does not scale for this future. What we need to do is, just as we use components in software development and services and service-oriented architectures to speed up the development of our software, we need to encapsulate our simulation models into components. We call them simulation components with defined interfaces. And we need to find a common set of these interfaces, because if every simulation component defines its own interface type, that makes no benefit. And it's only beneficial if we find a unified set of interfaces, an agreed set of interfaces that are accepted in the both simulation and architecture communities. Simulation component interfaces enable reuse. These interfaces should express capabilities of simulation components. The simulation component that has several capabilities, for example, for movement simulation, for Wi-Fi simulation, can expose several interfaces. Based on these simulation components, we can create simulation scenarios as templates that provide placeholders for required components, that provide common links, and that give engineers a starting point for creating their own simulation scenarios. Because in our experience with our customers regarding simulator coupling, we have learned that it's not to underestimate the challenge of instantiating a coupled simulation, even if you have simulation components already available. So these templates will simplify the creation of common simulation scenarios. We need to define abstract component types. So for example, an abstract component type for movement simulation that can then be specialized with concrete movement simulation models. And then it is not so relevant whether people are using one or the other movement simulator, as long as the components implement the same interface. We have already seen that this component approach simplifies simulator coupling significantly. It's only a starting point. This is the framework for the creation of simulation components. We are at the moment working on defining interfaces and also defining capability models that describe simulation components for simulator couplings. And we would like to invite everybody to join us in this journey, get in touch with us. Let's start to exchange our thoughts, our knowledge, and to develop together such a set of interfaces that enable simulator couplings. Thank you.